In the previous class, we looked at hydrogen bonding, so that is where we left. So in this one now, we are going to look at the structure of substances. So the structure of substances under chemical bonding, we have different types. One is simple molecular structure, then we have giant covalent structure, and we also have giant ionic structure. These structures are just building on the main types of bonding that we had in this topic, which were covalent bonding, ionic bonding, and maybe some other components of metallic bondings. Now, as we want to start with this, under simple molecular bonding, we say that it composed of small molecules containing small group of atoms held together by covalent bonding. In this case, now we just have some few atoms combining together to form a simple molecular structure. A good example we have under this is chlorine. Chlorine, remember, it is a combination. Chlorine molecule is a combination of two chlorine atoms. So we have one chlorine. So this is a chlorine atom. This chlorine atom combine with another chlorine to form chlorine molecule. So we can illustrate this using a covalent bond. So this is a chlorine, this is another chlorine. So the combination of the two, so this now is what is giving us chlorine molecule, a combination of the two. That is an example, a simple molecular structure. Another one, we have ammonia molecule, which of course I had explained in the previous class that it composed of one nitrogen and three hydrogen atoms combining together. So that one is also an illustration of a simple molecular structure. The second part, we are going to look at a giant covalent structure. What makes it a giant? So it is a giant in the sense that we have large number of atoms which are linked in a regular three-dimensional. So the key word here is three-dimensional arrangement by a covalent bond. Good example, we have graphite, we also have diamond and silicon dioxide. In this case, we have the same atom. For example, in the graphite or diamond, we have the carbon atoms. These carbon atoms, they are arranged in a particular order. That arrangement in a three-dimensional is what is making it to be called a giant covalent structure. Remember, still under this giant covalent structure, we are talking about nonmetal elements. Those arrangement, but all of them are nonmetal elements. Then we have giant ionic structure, giant ionic. This will be building more on the ionic bond, where we said ionic bond is formed when we have one metal element and another one as non-metal element. So the combination of metal and non-metal element forms ionic compound or ionic bond. So the structure of now giant ionic structure is going to be consist of positive ions, each surrounded by a regular arrangement by native ions. So that is the non-metal ions. So if we have one positive or charged ion, which is, for example, you can have sodium, being surrounded by non-metal elements. For example, we can have chlorine. That will be forming what is called a giant ionic structure. So for illustration, for example, I can be having, remember I'm explaining this concept here. So we have this end, this is our sodium ion. This sodium ion, we have chlorine here, we have chlorine. So we can see that sodium, which we know is a positive ion, then there will be chlorine. Which charge is chlorine? Which is a negative. This one is also a negative, this is a negative, this is also a negative charge. That structure is now what is called a giant ionic structure. Now, after giant ionic structure, now let's look at carbon as a macromolecular element. Carbon as a macromolecular element. We have looked at carbon in form 2. In form 3, we also built on some concept about carbon. In Form 4, now we are going to look at some unique properties or unique structures that we can obtain from carbon. So we say carbon is made up of two allotropes. The allotropes of carbon, the major ones are graphite and diamond. In the diamond we have 4 strong covalent bonds. So we have 4 strong covalent bonds within other carbon atoms. So in the diamond, it is a unique type of allotrope of carbon where we see that now there will be strong 4 covalent bonds formed between the carbon atoms. The atoms form a giant 3-dimensional lattice of strong covalent bonds. So there will be arrangement of these 4 covalent bonds of diamond. That arrangement will be forming what is called a lattice of covalent bonds. I can give a simple illustration. Of this where we have, so this is one carbon atom. There is another carbon atom here. We have another carbon atom. We have another carbon atom, then we have another carbon atom. So there is, sorry, let me draw it well so that we can see what is happening. So we can see this structure. So we have 1, 2, 3, 4. These are 4 strong covalent bonds which are formed. So in this kind of bond, we form what is called a diamond. This is just a 1-dimensional, but in page 95, you can have the diagram of covalent bonding with the 3-dimensional. So you will check on this so that you can build on the concept of diamond as an allotrope of carbon. Let's look at the properties of diamond. The property number 1, it is very hard. From the word hard means it cannot break easily. Now, in this case, diamond is used to make some cutting equipment or drilling equipment. The property that makes it to be used that it is very hard material, so it cannot break. It cannot break very easily. So when we want to make some glass cutting equipment, we use diamond. Number 2, it has got high melting point. Since the 4 covalent bonds are very strong, they cannot break very easily. That makes diamond to have a strong covalent bond. And that strong covalent bond will require more of heat energy to break. It is estimated that the boiling point of diamond is 3,700 degrees centigrade. As we can see, that amount of energy is very high. Then number 3, it does not conduct electricity. Diamond does not conduct electricity simply because all the valence 4 electrons are used in the bonding. So there is none which is free or there is none which is delocalized. Therefore, the diamond is an example of a poor conductor of electricity because the ions are not free to move or to within the structure. Then number 4, it has got high density. Carbon has got a higher density compared to graphite, and the density of diamond is about 3.5 grams per centimeters cubic. I think if I talk about density, you learned more of density in physics and even in chemistry. So we say in physics, how do we get density? Density is given by mass divided by volume. So that's why we have the unit to be grams per centimeters cubic. Meaning in diamond, we'll be having a larger mass, then we divide by a smaller volume. That makes it to have a higher density of 3.5 grams per centimeters cubic. Let's look at graphite. Graphite is another allotrope of carbon. Under graphite, we'll be looking at some unique comparison between diamond and graphite. Let's start with the definition. We say in a graphite, each carbon atom form three single covalent bonds to other carbon atom. So remember, in diamond, we say we were forming 4. in graphite now we form 3, meaning there is 1 electron that is not used in the bonding. That free electrons make diamond to have what is called a delocalized or a free electron that can move within the structure. So for example, we have some properties of graphite which might be totally different from what we had in the diamond. Number 1, good conductor of electricity. Why is it a good conductor of electricity? It is a good conductor of electricity because we say it forms 3 single covalent bonding. So there is 1 free electron. That free electron makes graphite to be used as a good conductor of electricity because it can conduct electricity. So it has got a free or delocalized electron. Number 2, lower density of 2.25 grams per centimeters cubic. In comparative with the diamond, which had a higher density of 3.5, graphite is now having a lower density, which is 2.25 grams per centimeters cubic, meaning the mass and the volume of graphite, we see that now relatively we have a larger volume as compared to the one that was in diamond. Then number 3, it is relatively soft as compared to diamond. Diamond had a unique property which we say that it was a very hard material. Graphite, on the other hand, is not hard. So that's why we are saying it is relatively soft as compared to diamond. Then graphite is used in lubricant industry, or it can be used to make some substance. For example, we have pencil that we normally use for drawing and writing. So that one can be made from graphite simply because it is a soft materials as compared to that, and also it has got a lower density. Finally, we say that it is insoluble in water. Solubility. So graphite cannot dissolve in water. This marks the end of this part where we were looking at carbon as a macro. Macro simply means that it composed of other allotropes, for example, diamond and graphite. So those are the major concept that we are supposed to learn under carbon and its component. In the next class, we'll be looking at now the metallic part. So far we have done more of covalent and ionic. The part that is now remaining for us to end this chapter is the part of metallic bonding, metallic structures. How does it look like? What are some of the properties of metallic structures? So that is what we'll discuss in the next class. Thank you. So this is a continuation of what we were doing before. Remember, the last part we were looking at diamond and graphite. So in this part now, we are going to look at metallic bonding. Remember, in the introduction we said chemical bondings, we had 3 main types of bonding. That is metallic bonding, ionic bonding, and covalent bonding. So we want to look at the last concept, that is metallic bonding. So metallic bonding occurs when we are talking about pure metals or their alloys. So when we have pure metals, we have what is called a metallic bonding present, or the alloy of those metallic substance. Alloy is formed when, for example, we combine different, for example, we take a pure element, we combine with another one so that we form an hybrid between the elements. Now, let's look at the diagram. In this diagram, we have positive ions and we also have the electrons. So the ones with the positive represent the metal, which is silver, for example. Then the ones that are represent with this earth represent free electrons. So there is that combination within the structure. We have the positive ions being surrounded by those electrons. Now, the major properties of metallic bondings. I think under properties of metals, we have looked at this one from Form 2. In Form 2 and Form 1, there is an introduction about properties of metals. Then in Form 3, we also learned some properties of metals. Finally, in Form 4, this is the last part that now we are going to talk about the metals. So we are going to look at properties of metal depending on metallic bonding. So with one, they are good conductors of electricity and heat. Electricity simply means that we can use metals to connect some electric cables, for example. Then a good conductor of heat, we can use metal substance, maybe for cooking, so that they good conductor of heat. Then they are also very strong. Very strong simply means they cannot break easily. Then they are malleable. Malleable means that we can hammer them to change to different shapes. So we can have different shapes. Maybe we can have the ones which are oval, we can have others which are rectangular, others. So we can have different by hammering or using a hard substance. Then they also have high boiling and melting point. So all metals have high boiling and melting point. This is because they are very hard and they require a lot of heat energy to break the bonds that within the metal structure. So that brings us to the end of this topic of chemical bonding and structure. So in summary, this topic was just trying to talk about how do these atoms or these molecules combine together. In that case, we look at maybe the diagrams of how the structures look like. We looked at the types of the bonding that we can have between if they are molecules, that is if they are non-metal elements or when we have the metal element. The combination between metal and non-metal, we form what is called ionic bond. Ionic bond gave us what is called ionic structures. When we come to covalent, we were looking at the combination between atoms where both of them are non-metal elements. The covalents gave us giant covalent structures and also giant molecular structures, as we described in the previous class. Now, in summary, in metallic bonding, now we say that it is formed when now metal elements, when we only have the metal element. This metal element can be pure metal element or the alloy of those metal elements. Thus brings us to the end of this chapter. Thank you for your time.